So please, when you're ready.
Uh, so first and foremost, I would like to thank Mauricio and Marcus for inviting me to give a talk. Uh, what I'm going to do is talk about something very fundamental, and that is the coherent forward scattering of neutrinos. Now, I know this topic has been covered somewhat in the lectures by Gabriela, but we will just try to get some more insight into the topic. So this is the outline of the talk. What I'm going to do is first talk about neutrino oscillations in general. I will just spend very short amount of time on this. Most of the talk I will focus on the matter effect, what it is, what it does, how it arises, etc. And the matter effect arises due to interaction of neutrinos with the matter in the surrounding medium. And that changes the neutrino oscillation probabilities. But there is an analogous effect called neutrino self-interactions, which occurs because of the interaction of neutrinos with other neutrinos. So I will also briefly talk about that phenomenon. Okay, so to begin with, let us just look at neutrino oscillations. What are neutrino oscillations? When neutrinos are produced, for example, in the atmosphere or in the sun, what happens is that neutrinos are produced because cosmic rays hit the Earth's atmosphere. And the byproduct of that is neutrinos, which are produced in the upper layer of the atmosphere. And you can look at these neutrinos will pass through the Earth, and we can detect it a few thousand kilometers away from their source. Now, because they have traveled such a long distance, what happens is that the flavor of the neutrino that we detect in the detector may not be the same as the one that is produced, and that is what we call neutrino oscillations. And since the neutrinos have passed through this matter, which the Earth is made up of, the neutrino oscillation probabilities are modified. Okay, and that is what we call the matter effect. And a similar thing happens in the core of the sun, where the neutrinos are produced in the center, and unlike photons, which will find it difficult to escape, the neutrinos just go through the sun in a straight line without scattering. And there also, it will interact with matter, and we will see some effect on neutrino oscillations. Now you'll notice I'm saying two contradictory things. I'm saying, oh, the neutrinos don't interact, they travel through a straight line. But at the same time, I'm saying the neutrino oscillation probability is affected by matter. So in this talk, we'll discuss why that is the case. Another scenario where neutrino oscillations are important is core collapse supernovae. So let us first discuss what is core collapse supernova. A core collapse supernova is the cataclysmic death of a star which weighs more than 8 solar masses. That is, it weighs more than 8 times the sun. Now, in that case, neutrinos are very important because 99% of energy that is released by a supernova is in the form of neutrinos. So it is very important for us to understand what the neutrinos are doing inside a supernova to understand supernova itself. And in the supernova, what happens is that in the deep interior, near the core, the densities are so large that the neutrinos get trapped. They are undergoing random walk, actually. Slightly outside, where the density falls, they start traveling in a straight line, but still they experience this matter effect and neutrino self-interaction effect, which changes the neutrino oscillation probabilities. Okay, and we have to understand what the flavor of the neutrino is, because the cross-section of neutrinos depends on the flavor. So it can affect the dynamics of supernova. Okay, So let us begin with the basics. You already know all about this, but let's just recap briefly. So how do we figure out how neutrino flavor evolves? And we do that just by looking at the Schrodinger equation. Now here, I'm just using the two flavor approximation. We know there are three flavors of neutrinos, but we are going to assume there are two flavors just to make the equations simpler. And how does the neutrino flavor evolve? We start with a wave function of electron and muon neutrinos. We know the tau neutrino. And we solve the Schrodinger equation to figure out how the wave function of each flavor evolves. So this Hamiltonian H has a very simple form. It's a 2 by 2 matrix with two parameters in it, the mixing angle and the frequency. The frequency depends on energy and the mass square difference. And this is a constant which we have to measure in a lab or some experiment. So once we solve this, what do we get? So this is the Taylor series expansion of the previous equation. And what we can see is that at a given time, the wave function of electron depends on the wave function of the electron at earlier time and the wave function of the muon at the earlier time. So there are two competing amplitudes. You can have amplitude which is trying to preserve the neutrino flavor, and then you have an amplitude which depends on the off-diagonal components of the Hamiltonian, which is trying to change the neutrino flavor. And there is a competition between them. And the amount of neutrino flavor conversion will depend on which one wins. So this is the wave function. So it is a complex number. What we want to find out is the probability of survival or probability of transition. And that we can get using this formula. Okay, so this is the overlap of the neutrino wave function with the initial wave function modulus square. So this gives you the oscillation probability or the survival probability. Okay, so this is the neutrino flavor oscillation formula in vacuum. When we have neutrinos passing through matter, what happens is that the Hamiltonian is modified. We have to take this 2 by 2 matrix and add this term to the Hamiltonian. Now, in most scenarios, the number density of positrons is negligible, so we can ignore them. So we just have this term. Okay. And you have already seen this in the second talk by Gabriela and the phenomenological consequences of this term. But what we are going to do right now is figure out where this term comes from. What is the origin of this term? Okay, so this term is arising due to a phenomenon called coherent forward scattering, which is just a fancy term for refraction. So when the neutrinos are passing through matter, they are experiencing refraction. Now, this coherent forward scattering is happening due to three different phenomena. Okay, like three different terms are present in this description. One is that it is a scattering. So the neutrinos are scattering with matter. Second is that the scattering is coherently enhanced. Now we will discuss what we mean by coherently enhanced. And the third is that it happens only the forward direction. That is why we call it coherent forward scattering. So we will look at each of this term one by one and figure out, gain some insight into this phenomenon of coherent forward scattering. So first and foremost, what is this scattering about? So there are two kinds of scatterings the neutrinos can undergo in matter. One is a neutral current scattering by exchanging Z bosons. Now, as far as this scattering is concerned, it is the same for all flavors, electron, muon, tau. So it does not affect the neutrino oscillation probability. So in most cases, we can ignore this. Also, as I mentioned before, there are barely any positrons in the systems we usually are interested in. So we can ignore this term also. The most important one is this term. So if you look at this term, this Feynman diagram can exist only for incoming electron type neutrinos, not for muon type neutrinos. So this will affect only electron type neutrinos, and that affects the neutrino oscillation probability. But this is just a scattering term. Okay, how is it related to coherent forward scattering? In order to understand that, let us first look at what we mean by coherence and what is coherent enhancement. So in order to understand that, let us look at our first introduction with coherence. So if we think about the interference experiment, just simple interference experiment from Feynman Lectures in Physics, Volume 3, the book you will see has two figures. I've taken these figures from there. And imagine you have a double slit experiment where you're shooting bullets from a gun. By bullets, we mean classical objects. And we are trying to determine how many bullets end up on the screen as a function of the displacement from the center. Now, if the bullet passes through slit number 1, you get this probability distribution P1. If it passes through the second one, you get P2. And if you add both of them, you get this P12. And you don't see anything fancy. But instead of classical objects like bullets, if we decide to shoot electrons through this double slit experiment, what we'll see is that if the electrons pass through slit number 1, you get this P1 distribution. If they pass through P2, you get P2. But if they pass through both of them simultaneously, you get this pattern, P12. Now notice something interesting. If you look at the height of this peak in the center, it is larger than this peak. So just because the electrons pass through both the slits simultaneously, you get a coherent enhancement of the intensity at the center. And that is what we mean by coherent enhancement. Now, it is very important that the electrons pass through both the slits. And we should not be able to figure out which slit the electron passed through. So this is the same figure as before, but now we modify the experiment and put a light source right here. And the reason we are doing that is because we're trying to figure out which slit the electron passed through. Because if the electron passes through slit number 2, while it is passing through the slit number 2, the electron gets illuminated by this light source. I can figure out which slit the electron passed through. And the moment I try to figure out which slit the electron passed through, the interference pattern disappears. So what that means is that in order to have a coherent enhancement, I should not be able to tell which slit the electron passed through. Now the same thing happens when electrons pass through a gas of electrons. So imagine this kind of a system where you have a gas of electrons. It's a thermal gas, and we have an electron neutrino wavefront approaching this gas. Now, as the wavefront passes through the gas, what happens is that the neutrino scatters off each of the electrons. Not one or the other, but all the electrons simultaneously. So we have a scattered amplitude due to the first electron, scattered amplitude due to the second electron, third electron, etc., etc. And what we need to do is add the scattered amplitudes from all the electrons. The result is this dashed magenta curve, which is also a plane wavefront, same as what went in. So we have a wavefront which went in, a plane wavefront which came out. What changed? Well, what changed is that if this electron gas was not present here, the wavefront would have come out with a different phase. So all these electrons are doing is changing the phase of the wavefront, which is going in. So the neutrinos went in, came out with the same momentum, but they passed through the potential. They experienced the potential exerted by the electrons because the neutrinos interact with electrons via weak interactions. So since they spent some time experiencing the potential, there's a phase shift. So we can just think of the coherent forward scattering as neutrinos passing through a potential. And as you know, that when a wave function passes through a potential, inside the potential, what is happening? The neutrinos are spending time in the potential, so its kinetic energy or its wavelength has to change. So when it comes out with a phase shift. Now, why is that important? Because this is exactly what happens in optics. This is exactly what Huygens principle tells us, that when light passes through a medium, each point in the medium acts like a source, and the result is refraction. Now you may say, but we just said the neutrinos don't change their direction, they only have a phase shift. Here you can clearly see there is a change in direction due to refraction. And the answer is, when we look at neutrinos passing through a medium, the index of refraction is extremely small. It's like 10 power minus 6 or something of that sort. So we can completely ignore this bending, and we can just focus on the phase shift, that is the change in the wavelength that happens due to refraction. And why is that the case? The reason is we have to look at neutrino oscillations again. Why are neutrinos oscillating? Let us think of a neutrino wave function. So if we look at the wavelength of a neutrino, which has energy of around 10 MeV, its wavelength is 20 Fermi, okay, of that order. So if we have a neutrino, a flavor eigenstate of neutrino emitted in a weak process, it's a linear combination of mass eigenstates. Since the two mass eigenstates have different wavelengths, slightly different wavelengths because they have a different mass, what we observe is a phenomenon of beats. And that wavelength of beat is a few kilometers. That is what we observe when we call neutrino oscillations. That phenomenon of beats is what we are observing. And when neutrinos pass through matter, its wavelength changes ever so slightly, but the length over which the phenomenon of beat happens changes quite dramatically because of this relationship. So now let us look at, but why is this important and not the scattering? So if we look at the amplitude we earlier looked at, it has three contributions, right? One is order of the vacuum frequency that is coming from the vacuum Hamiltonian, right? Then there's a scattering amplitude, which is coherently enhanced. That means it's proportional to how many scatterers are present in the matter. And then there are momentum changing scatterings, where the momentum of the neutrino changes so much that imparts a big recoil on the electron. So I can know which electron is responsible for scattering. Coherent enhancement does not happen. So that is this third component. Okay. So if I want to find out flavor transition amplitude or probability, sorry, I have to take this and take a modulus square of it. Now, what we normally do is we take this and this together because those are coherent processes. And this here, what we do is we first square it and then multiply by the number of scatterers. Okay, so if we look at only the coherent piece, what we are seeing is that we have an interference term which goes like omega GF. So we have a term in the transition amplitude which goes like first order in the Fermi constant, whereas the momentum changing scattering goes like GF squared. And that is why when we look at a system like the sun, the incoherent term, that is the momentum changing process, is not that important. But the coherent forward scattering is important because it goes like GF, whereas the momentum changing term goes like GF squared. Okay. Now, all this is fine. But what about neutrinos interacting with other neutrinos? The same thing happens, and the phenomenology is even far more interesting. So let us look at the interaction of neutrinos with other neutrinos, which can happen because neutrinos can exchange Z boson. So in that case, we have to add a Hamiltonian to our Schrodinger equation, just as before, but the Hamiltonian is a bit more complicated. So the reason why it is complicated is because, as you noticed earlier, the Hamiltonian depends on the flavor of the medium, the flavor content of the medium. And here, the neutrinos are interacting with other neutrinos in the medium, and their flavor is changing dynamically. So we have to take care of that. So because of this, the Hamiltonian depends on the flavor of the neutrinos in the medium, which makes the equations of motion non-linear. And that gives rise to very rich phenomenology. So let us try to understand this phenomenon again. Okay. So if we look at the same kind of picture we saw before, where there's a wavefront of electron neutrino approaching a gas of electron neutrinos, what we see is something very similar as before. You have a neutrino scattering of electron neutrinos. There is a coherent enhancement in the forward direction. But the amplitude of scattering now is twice, because there are two possibilities. The wavefront which approaches and is scattered by these electron neutrinos, or you can have a momentum exchange. That is, it is possible that the neutrino which is coming out is one of the neutrinos which was in the thermal bath. So you have an exchange, and that leads to a scattering amplitude, which is twice in magnitude. But that is not that interesting. What is interesting is this case. So let us consider a wavefront of electron neutrinos approaching a gas of muon neutrinos. Now what happens? Can we have a scattered wavefront which is contaminated by muon neutrinos? The answer is yes, but it is not coherently enhanced, because notice what happens. If a muon neutrino comes out, the only way it can happen is if one of the neutrinos in the thermal gas changes its identity. So one of the neutrinos in the thermal gas changes from muon neutrino to electron neutrino. Only then a muon neutrino can come out. So I can identify which scatterer was responsible for this scattering. Okay. So in this case, coherent enhancement is not possible. You cannot have a coherent forward scattering. But what happens if instead of just muon neutrinos in the gas, I have a linear superposition of electron and muon neutrinos? In that case, if an electron neutrino goes in, a muon neutrino can come out, and I won't know which neutrino was responsible, because it is a superposition. And that way, we can have a coherent forward scattering, which is flavor changing, which is not possible in case of normal matter. Okay, and the result is a phenomenology which is extremely rich. So I'll just give you an example. So this here, what we see is angular distribution of electron neutrino and electron antineutrino. This x-axis is the angle. So one is radially outward and -1 is radially inward for a supernova emitting neutrinos. And as you can see, as time passes by, neutrinos and antineutrinos start oscillating in tandem. And there is no way to solve this analytically because it's a nonlinear equation. There is no pattern here. This just keeps going like this. And the astrophysical implications of this kind of evolution are still not understood because it's a very numerically heavy calculation to do. And usually we have to make some kind of assumption regarding the astrophysics of the system in order to do these calculations. For example, here I have ignored the axial angle. So you have to impose some kind of a symmetry to do these kind of calculations. So this is a very active field of research. So the takeaway message is that coherent forward scattering plays an important role in modifying neutrino flavor evolution. And the phenomenology that results from this coherent forward scattering is very rich and active field of research. As far as coherent forward scattering is concerned, there are quantum mechanical subtleties which are unsolved to this day. And work is going on right now as we speak to resolve these quantum mechanical subtleties, but I haven't talked about that in this talk. But if you are interested, we can have a chat later. Thank you.
Thank you, Shashank. Other questions?
Thank you for the talk. So, looking at the neutrino self-interaction processes you describe, it seems as though you're only considering flavor-conserving interactions, which we've, or maybe which we've discussed at length through with Gabriella, at least, that this does not necessarily need to be the case. So would anything change, or how would it impact to also take into account non-flavor conserving interactions?
By flavor non-conserving, you mean interactions beyond the standard model?
Yeah.
Okay.
Interactions where you change electron number or muon number, tau number.
Yep. So the thing is, yeah, that's a whole different issue. The thing is, right now we are just, I mean, there are so many quantum mechanical subtleties that we are trying to resolve that I think the focus in the field is trying to predict what happens within the confines of the standard model. But there are a few people looking at this kind of stuff, and the numerical simulations of this take such a long time that we have to be very judicious about what kind of problems we solve, right? So normally what happens is when we look at the theories beyond the standard model, you have a plethora of these kind of flavor violating models, and you have to choose one of them. So it becomes quite a difficult challenge to look at all of them because of the numerical, the complexity of numerical simulations involved. So there's not much work done on this topic, but right now the focus seems to be on the standard model processes.
Okay.
One
So, Shashank, you haven't really talked about supernova simulations and that sort of thing, but just very broadly, how difficult would it be to implement this kind of behavior in a full supernova simulation?
Extremely difficult because first and foremost, when we look at simulate a calculation like this, you see we need angular distributions. And these angular distributions are not present in the hydrodynamical simulation. So first we have to modify the classical, by classical I mean without neutrino oscillation, neutrino transport, to make sure they actually calculate the angular distributions. And then on top of that, add the neutrino flavor evolution. Any complication that is added to supernova simulations would be problematic, because if you look at a three-dimensional supernova simulation, it takes months on a supercomputer. So if you add anything to it, it's going to make it worse. Yeah, that makes sense. So what we are trying to do is understand the physics so that we don't have to actually do the full calculation. Yeah, makes sense.
Thanks.
So maybe on this one here, so what you showed on the right is this the Bloch sphere.
Yeah.
And do you pick out a
No,
certain
this
angle?
is just the integrated version of that.
Okay.
The
Integrated over the scattering angle.
yeah.
I see. Okay. So okay. Okay. Any further questions? Yep.
This might be maybe a basic confusion I'm making, but on the slide where you showed, maybe it was 21 or something, where when you showed the fact that you can identify the neutrino inside of the thermal bath, which produced this flavor change. If the neutrinos are scrambled inside of this bath, how in practice would you do this? How, I mean, in terms of the double slit experiment, it looks so practical, like
Yep.
you're seeing it, you know.
No, so the thing is, it's not about practicality, right? So imagine, let us look at the double slit experiment again, right? So the thing is, let us look at this experiment where I put a light source, and what the light source is doing is it's illuminating this electron, so I can tell which slit the electron passed through. But I don't have to look for the light, scattered light. The moment I put the light source here, the interference pattern is gone. I don't have to actually look at the scattered light and figure out which slit the electron passed through. Just the fact that it is in principle possible for me to determine which slit the electron passed through is enough to kill the interference, right? The same thing happens. Here. I don't have to actually figure out which particle was responsible. Just the fact that you had a gas comprised of muon neutrinos, one of them shifted to electron neutrino, I can in principle figure out which particle was responsible. That is enough to kill the coherence. There is no human involvement in this process, right?
Yes.
Yeah.
Thank you.
What happens here if you have another muon neutrino? Sorry, the initial state is electron.
Yeah,
So if you have another electron neutrino which erases now the red one back to a green one, that could also potentially be indistinguishable, right? So this could like a higher order effect.
Okay. Everything we are talking about is first order.
Yeah.
The higher order effects will go like GF squared.
Yeah,
So
of course. Yeah.
they will be negligible. Yeah.
Okay. No further question. Let's thank Shashank again. And so this brings us to the end of almost the end of our summer school. Now, Maurizio had actually prepared some slides, but he's probably picking up some lunch right now. So maybe that's probably more important for you. So, but we have already Christian sitting here in the audience. So Christian is a member of the Niels Bohr archive. And we have asked him also to give you a bit of a historical perspective of the Niels Bohr Institute, Niels Bohr's life. And maybe since Maurizio is not here at the moment, maybe we can start this first. So Christian has prepared a presentation. Yes. Do you want to use your laptop? Yeah.
cool if I can. But running on it, right? So
right.
transfer that quickly.
Yes.
I don't have.
Okay. I have to use this.
But it's yeah. Thank you. Problem is, I have one of these new Macs with USB 3. You come prepared. Good.
I have a USB stick with this one. Yeah.
And it has Keynote running on it, right?
Yes. Yes.
Good. Good.
So maybe.
And that's actually, yes, so wow, it's not a sanitized version, so there's many slides you're not supposed to see in that, but I trust you'll just delete it later, right?
Yes.
I
I can just run it from the USB stick and I give it back to you.
should be here somewhere. It's called Neutrino Summer School. It's 110 megabytes, but it goes fast. Perfect. Doesn't want to get ejected. Yeah, now it is.
Okay.
Now you take over. So I'm not able to see my slides then, or what is?
You will see the slides. Yeah.
Okay.
Wait, this is the stick. This is the.
Ja, wir können keine Aussprache.
Wir können auch Sommerdeutsch hier.
Aber wenn es jetzt bei dieser Anzahl hier bleiben sollte,
Dann
aber eine
vielleicht mit einer schon, ja? Ja, weil
also
am letzten Tag ist es oft so, dass viele.
Leute schon 1, 2, 4, 6, 8, 10.
Es war 25 oder so, hatte ich da gezählt.
Jetzt sind es 22. Das ist der ohne Bildung.
So,
Es gibt auch dieses Präsenztool. Kann man schon ausprobieren.
das, sorry.
Hi. Mauricio. Yes. Oh, I know your name. Sure. Absolutely.
So the early pages. Yeah. So we reverse it. No? So that's
There is a historic site with the same last name. Yeah, but I'm not related. Okay. Maybe. Yes, it's But you have some slides, so I don't mind. I don't know.
I think we go first with you, yeah? So this is it.